You're staring at it right now and you don't even realize it. Every single day, trains carrying 6 million pounds of weight, that's heavier than the Statue of Liberty times 10, blast across a strip of steel at 70 miles per hour. No wings, no suspension, no cushion, just steel on steel. Screaming down a track that was engineered to within a fraction of a millimeter. And here's the thing that should stop you cold. That track you're seeing? It didn't start as a track. It started as a pile of dirt. Actual dirt. Pulled out of the ground, melted in fire hot enough to vaporize your hand before you even got close. Beaten, stretched, tested, and cut into something so perfectly engineered that it has to be right. Because if it isn't, 1 millimeter off. That's all it takes. 1 millimeter, smaller than the thickness of a dime, and a fully loaded freight train goes flying off the tracks at highway speed. So today we're going step by step through exactly how a railway track is made. From a hole in the ground to the finished steel rail carrying 200 miles per hour of force. You will never look at a train track the same way again. Let's go. The journey starts underground, literally inside the earth. The main ingredient for a railway track is iron ore, a naturally occurring rock that contains iron atoms locked inside it, mixed with other minerals. It looks like a rusty, dark, reddish-brown stone. Completely ordinary. You'd walk right past it on a hiking trail without blinking. But locked inside that dull rock is the raw ingredient for one of the strongest structures ever built. Iron ore is mined in massive open-pit mines, enormous holes in the ground the size of small cities. We're talking dump trucks so big that their tires alone are taller than a 2-story house. The ore gets crushed and ground down until it's separated from the useless rock. What's left, pure concentrated iron, gets formed into small pellets roughly the size of a marble. These pellets are what gets fed into the next stage, and the next stage is where this story goes from interesting to absolutely extreme. The pellets get loaded into a structure called a blast furnace, a giant industrial tower over 300 feet tall. It burns continuously 24 hours a day, 7 days a week, for years without stopping. You don't turn a blast furnace off. Once it's running, it just runs. Inside, the pellets get blasted with superheated air. Temperatures hit around 2,900 degrees Fahrenheit. Your oven at home maxes out around 500. A blast furnace is nearly 6 times hotter. Hot enough that the iron literally melts out of the rock and sinks to the bottom. That liquid iron, glowing orange, thousands of degrees hot, gets drained out and poured into enormous ladles. Some of these ladles hold over 300 tons of liquid metal at once. But this is not steel yet, it's pig iron. Pig iron is too brittle to build anything with. It would crack like glass under the weight of a train. To get from here to a railway track, that iron has to be turned into steel. To convert liquid pig iron into steel, it gets poured into a basic oxygen furnace. A giant tube blasts pure oxygen into the liquid metal at supersonic speed. That oxygen burns off the excess carbon in a massive reaction. Railway track steel is special. It has to be incredibly hard on the surface so wheels don't wear it down, and slightly flexible inside so it doesn't shatter. Getting that balance requires metallurgists who precisely adjust the chemistry. The liquid steel is poured into a continuous caster. As it moves through a water-cooled mold, the outside solidifies first, forming a hard shell. What comes out the other end is a solid rectangular block called a bloom. These blooms are 16 inches square, dozens of feet long, and still glowing a deep orange at 1,800 degrees Fahrenheit. They look like giant rectangular bars of metal. To turn them into tracks, they must be squeezed and stretched. The blooms are reheated and fed into a rolling mill, a series of enormous steel cylinders that the bloom passes between, over and over. Each time the rollers squeeze it into a longer, thinner shape with thousands of tons of force. A rail looks like an upside-down capital T. The head is the thick surface wheels roll on. The web is the vertical section. The base is the wide foot that sits on the ties. This shape transfers the train's weight directly into the ground. After rolling, the rail is cut to standard lengths, up to 240 feet. Then they go to a cooling bed. This matters because if one side cools faster, the steel warps. Air must circulate evenly around the entire rail. Even perfectly cooled rails develop a slight bend. That's why every single rail goes through a straightening machine. rollers that bend the rail back and forth until it's perfectly straight within a fraction of a millimeter. The most dangerous flaws are hidden deep inside the steel. Engineers use ultrasound, the same technology used in hospitals, to see inside. The probes send high-frequency waves that bounce back if they hit a hidden crack or void. Every dimension is measured with calibrated gauges. Samples go to a lab where machines try to literally break the steel. If a rail fails any single test, it doesn't ship. Period. Accuracy here is the only thing preventing disaster. Modern tracks don't have the old clickety-clack joints. Sections are welded end-to-end using flash butt welding. A massive electric current heats the joint to 4,500 degrees, and the ends are pressed together, fusing them into one piece. These are called continuously welded rails. Eliminating joints reduces maintenance and prevents the cumulative fatigue caused by wheel impacts. It's a smoother, safer ride for the heaviest freight in the world. Before the rail goes down, the foundation is key. Railway tracks rest on crushed granite called ballast. It distributes weight, drains rainwater, and allows engineers to adjust the track level by adding or removing stone. Steel expands when hot and contracts when cold. In the US, a quarter-mile rail can expand by 10 inches between winter and summer. If that stress isn't managed, rails can buckle outward. A terrifying event called sun kinking. The solution is installing rails at a calculated neutral temperature. This ensures the expansion and contraction push and pull equally. Special expansion joints at the ends allow for controlled movement without catastrophe. It's not just a track. It's one of the most sophisticated pieces of engineering hiding in plain sight. A piece of steel engineered to a fraction of a millimeter, holding the weight of the entire American economy. Which part of this hit you the hardest? Drop it in the comments. And if you want the next video on how we test these tracks at full speed, hit subscribe and the bell right now. I'll see you there.